Interferometers are a big topic here on the channel. It's possible to say that we're all a little obsessed with this idea that you can combine the light from multiple telescopes and create a virtual telescope equal to the separation between those telescopes. Now, we've seen this work with the Event Horizon telescope and the radio waves, and there are even interferometers that work in other wavelengths, including infrared. But there is an interferometer that works in visible light. And this is the CHARA array, which has been operating for about 20 years at Mount Wilson Observatory just outside of Los Angeles. I've been very curious about this interferometer because it is visible light. It is one of the more complicated ways you can try to create a virtual telescope. And yet this has given us incredible views of rotating stars, calculating the separations between binary stars. It has incredible strength, and it also has some limitations. My guest today is Dr. Nic Scott. He is a telescope system scientist for the CHARA array, which is funded by Georgia State University and the National Science Foundation. And Nic works on instrument design in helping to upgrade and improve the CHARA array. 6 individual 1-meter telescopes acting as if they are a telescope 300 meters across, the biggest visible light telescope on the planet. And they're adding even more upgrades. They've got a mobile telescope that they can move around, potentially up to 1,000 meters away, to add to the array to increase its resolution. So if you're interested in interferometers, and I know you are, then enjoy this conversation with Nic Scott. Nic, can you give me a sort of, I guess, a virtual mental tour of the CHARA array? Where is it located, and how is it situated?
Sure. It's a really unique location in that it's on Mount Wilson Observatory, which is a historic observatory outside of Los Angeles. So you don't often have such a large observatory right next to a major metropolitan area. It's at 5,700 feet. It's about 40-minute to an hour drive from the outskirts of LA. We're surrounded by some of the most historic telescopes in the world. So the 60-inch telescope, the 100-inch Hooker telescope. This is the place where Hubble and Shapley worked and discovered that the universe was expanding. And then within that historic observatory, we have the CHARA array. And so we've got 6 1-meter telescopes, but they're spread out across the mountain in a Y shape. And they go from kind of the edges of the cliff to edge of a cliff to a place where we could go a little further in the southwest and east directions. And on each one of those arms, there's 2 of these telescopes. And it's in what's called a non-redundant configuration, so that the distances between them are all different. And we do that for interferometric reasons. And then there's vacuum pipes between. So these pipes are about this big around that lead between the bottoms of each of these telescopes. Some of them are on towers. Some of them are at ground level. A couple are underground. And they all go into this long beam combining lab. And this lab is this long rectangular building, and the pipes all have mirrors inside. They're all in vacuum because we're sending light along the ground, and that's where the worst seeing is, so the worst turbulence. So we evacuate those tubes. And eventually we get those pipes all lined up in a straight line going down that optical path length compensation facility. And then they come out of the light comes out of a periscope. And then we have these long delay lines. So we have rails with these motorized carts on them that were built by JPL. And there's mirrors on them. And it's basically like an optical trombone. So while we're observing, right, if you use a telescope, it's a big clock. You have to compensate for the Earth rotating. Well, with interferometry, we have to also compensate for the path difference that distance the light takes. The only way to get interference is if the light takes the exact same path, or at least the same distance path, through all the telescopes. And so based on where we're looking, if we're looking to the east, the light's going to hit that telescope first. We need to slow down that light. We can't physically slow down the light, so instead we give it more distance to travel. And so the longest separation is between this S1 and E1 telescopes on different sides of the mountain, and that's 331 meters. And with an interferometer, it's not the size of your telescope that determines the small details you can see, it's the separation. So that 331 meters is as if we have the same angular resolution as if the whole mountaintop is one big mirror.
Right. I hadn't even thought of some of these things. So the fact that you're looking at an object that is to the right or to the west or to the east or whatever, that the amount of time it takes for the light, for that I guess for that same wavefront to enter all of the different
Exactly.
telescopes, you are now sort of off that resolution, and you need to compensate the distance between the telescopes
Yeah, you're not a
minutely.
fringe bracket. You're in an entirely different thing, and you're not going to get any. We call them fringes.
Right.
That's the bands of light and dark. It really CHARA goes. It's a Michelson interferometer, which goes all the way back to like Young's double slit experiment. So we were looking at bands of light and dark, and if you do that in enough different ways, you can build up an image of your object, and you can measure things like the diameter of a star directly.
Right. And so what is this process? So the sort of the tuning process of you to bring those telescopes back into alignment, how is it done sort of physically by an operator?
By the operator,
or by the computer that does it, whatever.
There's many different stages, right? We've got just for the operation during the night, if everything is already aligned and running, the light goes through the telescopes. We have adaptive optic systems at the telescope. So we have a deformable mirror, and that helps make up for some of the atmosphere we're under. The light then goes all the way through into the lab. So no one's in the telescope. There's one operator running the whole thing at night, usually one operator, one scientist. There's lots of alignments we do during the day to keep this all running. The light goes through all these mirrors. It goes through what's called POPs, it's short for pipes of pan, because we have fixed segments of delay based on where we put certain mirrors for chunks of the sky. And then the active delay, once it comes out into open air in the lab, the cart rolls along, and it can move up to 10 centimeters a second or so a second. So it can book it like pretty fast. Typically, it's rolling slower. There's a motor cart, which is what's driving it. It's not physically connected to the optics cart. It's what's on a voice coil, so like a speaker, so that there's not vibration transmitted. Because if you have ever looked into interferometry, vibration kills you. You're talking about, you have to get it to a fraction of the wavelength of the light you're looking at over the course of hundreds of meters. So any slight vibration, someone walking by the lab, a car driving by, will mess this up. People often ask if we detect, how do earthquakes affect us? I've been observing before, and you'll see the fringes just disappear. And then like, what was that? And you see, it was a 3 on the Richter scale,
right,
dozens of miles away. And then they come back. So light goes through this path. On that cart, motion of the cart is the first order correction after the fixed delay. The primary mirror on the cart is on another voice coil, and it has a eddy current sensor, so it can detect exactly where it is fairly well. And then it also it goes off a cat's eye reflector. So it's a parabola. It's a little mini telescope, basically. So that parabola, the main mirror can be adjusted, and then there's a piezo stack, so you can do really fine correction of distance, and that's where the very fine tuning of the optical path happens. And that reflects off the cat's eye, and then it goes down, and then we have a whole optical switch yard, and then it's about getting which telescope to which instrument. At the same time, we have a metrology laser that bounces off the cart, so that we can measure to within fraction of a micron, down to tens of nanometers or so or less, of where the cart is at any given time. So it's tracking the whole time. And all of that we have systems built in of lots of computing, lots of mechanics, lots of electronics, all having to work perfectly together to get that to work. And then once it goes to an instrument, we have multiple different instruments that, based on what science you're doing. And it may be open air, and they combine in the open air and then go into a camera and get detected. Or more common now is going into optical fibers or into integrated optic chips, and then going to the detector. Yeah.
And now I realize it's probably even more complicated than I'd originally, whether the object you're looking at is to the west, it's moving in the sky. Okay. And so the whole apparatus is compensating in real time. Yep. As the distance of the light is changing as it approaches zenith and goes the other way. You're having to just move this entire the telescopes are turning, and then the mirrors that are bouncing, the distance between the telescopes is slowly adapting to keep this thing being an interferometer.
Yes. It's a massive amount of work, and it's analogous to, if you've ever made a pointing model for a telescope, to get your telescope's never going to point perfectly right, and so you can, build up a catalog of stars and get your pointing very well. Well, we have the same thing. We have a baseline solution. So we have very precisely the distances to the telescopes. We're in fractions of a millimeter or many microns. We can actually measure. We have an annual meeting and we go through, how the array is doing and lots of different details. How the mountain is moving or how the telescopes are changing, or we also have to take mirrors out and recoat them every so often. So then the entire beam chain, you're looking at like 20 reflections before you ever get near a camera, which is why we look at bright targets. We have to take out all those mirrors, recoat them, and then replace them and align them all. So alignment is a big task here.
Yeah, that's amazing. All right, so let's talk about the kinds of targets, the kinds of observations, and sort of, as I explained interferometers to my audience, it's all about, as you said, the separation of the mirrors. That gives you the resolution, but the sort of the sensitivity comes from just the total surface area of your mirrors. And so if you've got 6 1 meter mirrors, that is a relatively small telescope compared to other giant astronomical observatories. And so what are the best targets for you to point the CHARA array at?
Sure. So the trade-off, like CHARA stands for Center for High Angular Resolution Astronomy. Like we care about the resolution. There are other places you can go much more sensitive, go deep. That's looking in other galaxies and these, deep field images. We, started out with binary stars, orbits of stars, diameters of stars. So it's kind of an evolution. The guy that kind of got the CHARA array rolling, my advisor, Hal McAllister, started in speckle interferometry, and it built some speckle instruments, and that's where you use a single telescope to do interferometry. With the Michelson type, what we can do is fundamental astrophysics. So really, it's the basis of everything in stellar astrophysics is stellar models, understanding how stars form. Now looking at how possible planet forming regions are. So like young stellar objects. Now we've moved on from just orbits and complex orbits and diameters to imaging stars themselves. So a lot of stars, there's a huge range in size of stars compared to the sun. It always usually shocks people when you show them that range. The sun has spots on it, but those spots are, about the size of Earth projected onto the sun. With some of these stars, it's 20 or 40% of the area may be a spot. And we can track their rotation. We have movies. Rachel Rodenbacher has done some incredible research where looking at imaging these spots on these stars and you see them rotate and how they're changing with time. And that feeds straight into the theorists. There's always this kind of interleaving in astronomy between the observationalists and the theorists. And, you can come up with many models, but you need to have these particular measurements to be able to eliminate some of those models or pin that down. So that's where observation comes in. And so we get a lot of that. The orbits are the only way you can really tell the mass of a star directly. It's very simple, gravitational, relatively simple. That if you have 2 objects orbiting in space, that they have you can tell what their mass ratio is and then get a physical mass. So that's why we weigh the stars. Other things are disks around stars. So now we're doing more imaging because if you just have 2 telescopes, you have one baseline, you can measure diameter and that's it. When you have 3, you can get what's called a closure phase and you can start to see if something is circularly symmetric or not. And when you start getting more and more, and what's nice is it goes up by the combination. So if you have 6, we have 6 telescopes, we actually have 15 baselines between them. So if you drew the lines all between, it's n times n minus 1 over 2. So when you add a telescope, it's more like an exponential increase in your imaging ability. That was actually one of the reasons we got a 6 telescope built when the array was first constructed. And imaging is really paying off. Most of our nights observing now are with these 6 beam interferometers that can do imaging. We have the newest one is called Spica, and it works in R band. So we're going all the way into stuff you can see with your eyes. And Merc-X and Mystic work in H and K band. And we've designed the array in such a way that you could do simultaneous imaging with all of these. So all these beam combiners work together.
Now, the kinds of targets that you would be looking at, I mean, what is sort of like the magnitude? Because could I go outside and look at with my own eyes in dark skies on the
easily everything you can see by eye we can do. Because
right.
Your eye goes down 6 magnitude. If you're perfect. We can get down to about ninth magnitude. So we have one beam combiner that's one of our new ones called Cimarel, and it's an upgrade of the first beam combiner we ever made. So the nice thing in how Georgia State got around getting the array built is kind of incredible. Of part funding from GSU, part funding from National Science Foundation, one telescope paid for by the Keck Foundation, and GSU paid and built one beam combiner. So we had one instrument. It was CHARA Classic. It was a very sensitive, just open air, going into a Dewar into an infrared camera, two beam combiner. And what we did is made a consortium. The array is unlike most facilities, and unlike I think every other interferometer, the few that there are, in that it's a complete collaboration. We have a consortium of multiple universities, multiple groups. You can propose, hey, I want to try this out, and come test it here. If we can make it work, we will try that. If it doesn't interfere with observations. So University of Michigan built the MERC-X and Mystic imaging combiners. We partnered with the Côte d'Azur in France, as well as the Paris Observatory. So we have two groups from France. The Australian National University and University of Sydney. So it's kind of Australia, France, and the US are kind of the main players in interferometry. Even now, Kyoto Sango University is using Cimarel to do non-stellar objects, to look at measuring the diameter of an AGN, an active galactic nuclei. And that's one of our big drivers for getting more sensitivity.
Right. I mean, these things are big and interesting, but faint compared to the bright stars.
Yeah, we can do the nearest, NGC 4151. But if you look at the number of targets, if you get them, it's nonlinear. You gain a magnitude, you get a lot more targets. Mm. So that's kind of the future I see, is wanting to upgrade the array. The array is 20 years old, 20 years since our first science paper. First fringes were in 2001. So I'm the telescope system scientist. I do a lot of work on the hardware, on the telescopes, and the alignment. But we all are a big Venn diagram of everyone works on everything. The thing that is a challenge is that we're not limited right now by technology. We're not limited by the theory. We are limited by resources. We could really be doing incredible things. So we have a project that's funded called CMAP. It's the Charleston-Michelson Array Pathfinder. And this is part of this vision for the next stage of the CHARA array would be this Michelson array. And that would be, we're moving and testing using optical fibers to connect the telescopes instead of the vacuum tubes, because it becomes cost prohibitive to have a giant vacuum tube going across mountains. When you want to do like a kilometer baseline, that's not going to really be feasible. So we're looking at different ways for beam transport. So we have this mobile telescope. We can double our current maximum baseline eventually and doing fringes through the optical fibers. But that fiber always has its own challenge.
Yeah. So can you talk about that mobile version of these? Because this is new, right?
Yeah, this is new. So our current telescopes, the 6 original telescopes, are more traditional. Like they were custom designed. They were designed in Tucson and built on site here by CWest. And they're a very rigid, very custom one-off design. Technology's evolved in 20 years. Now you can cut a check and you can buy a 1 meter, very nice telescope. So we bought a plane wave 1 meter telescope, and they're getting into like CNC milling their mirrors, and they're incredibly lightweight. So their mirror is it's like a third of the weight of one of our primary mirrors, but still just as good. And carbon fiber truss, really nice technology development. So what we did is we bought a plane wave 1 meter, and we built a custom enclosure around it and put it on a trailer, and then have hookups and a smaller version of our adaptive optics on it. And it is entirely for fiber feeding. It doesn't go into the vacuum pipes. It still can connect to the lab, but we've trenched across the mountain. We've laid fibers, and we inject light into those fibers. And they can combine then with all the other telescopes in the lab.
Wow. And so that process of bringing the images in from the mobile telescope, has that been effective?
We are very soon expecting our first on-sky fringes. We've gotten lab fringes through the full run of fiber. The weather and other technical issues have not cooperated recently. It's been a little hectic in California recently as far as weather and climate. But we expect it should be. It's been done in the past that there's been, interferometry through fibers. There was originally plans on Mauna Kea to connect all of the big telescopes by fiber. The Keck interferometer was running for a while, of connecting the two big Keck telescopes by an interferometer. So it's there's technological hurdles, but also a lot of those challenges we're looking at using integrated optics and partnering with optical engineers to make it go smoother than it has in the past. One of the big issues is dispersion through the fiber, because the fibers have different strains on them, and that's going to affect, you have all sorts of things that can reduce the contrast of your fringes.
And I mean, it's so difficult to just align the images from these emplaced telescopes that very, very well, to just have one on a truck that you're driving around, and then you stop and then have it join this network. I mean, wind blowing on the truck, the air pressure changing a little bit, a bird landing on one part of all of this has got to have an effect.
Yeah. So I actually designed the enclosure so that the entire telescope and its pier is the telescope and its pier is isolated from the truck and from the dome, and so there's no vibration transmitted. It has a huge concrete pad and the concrete pier below ground. So we basically, in the course of an hour or two, it transitions from a truck into a fixed telescope.
Right. Wow. And so what is the farthest distance you could take this truck from the rest of the array?
We are currently funded. We have it now. We wanted to add a new short baseline. So not just the longest is good, but having these shorter baselines. So we have a roughly 17 meter baseline added in a triangle. And we have another position ready that's at about 550 meters. So almost doubling our current resolution. And just for scale for people, like our current resolution with the 331 meters is equivalent to reading newsprint in New York City from Los Angeles. That's the kind of details of these English scales.
If it was very, very bright newsprint.
If it was very bright and very high contrast, yes.
Yeah.
That's the catch. So we have this, our second site is prepared and ready, and that's where we will move and do testing once we finish with doing the initial test at the 17 meter. But we've also identified a potential third site, which is actually off of the observatory grounds on the other side of the mountain where the Los Angeles Basin TV antennas are. There's a site that would give us an 1,100 meter baseline.
Wow.
And that would, it'd be absolutely groundbreaking.
Yeah. Then it's on the moon. You're reading that newspaper.
At that point, we're reading the period on the manual that was left behind, like the dot at the end of the sentence on the manual left on the moon by the astronauts.
Right. As long as it was as bright as a star.
Exactly.
Right. Yeah. Okay. So I think this gives people like a real sense of the array as it currently stands. And so now I want to sort of move into just interferometry in general, because it is easily one of the most popular topics on my channel. And I've had to become a sort of amateur expert in the limitations of interferometry, so I can at least, sort of kill the dreams of the people who ask.
Don't ask me to go
these questions.
Fourier equations on the blackboard on the spot.
Yeah. And so I guess what people always want to know is, why can't we just make ad hoc interferometers out of the enthusiasm and volunteer efforts of people around the world with their telescopes, or with Starlink satellites that are in space? Or why can't the world's observatories come together to create an interferometer like we saw with the Event Horizon telescope?
Sure. Well, the difference is the wavelength. It's kind of a regime change when you get from radio and get shorter and shorter wavelength. You move from what's heterodyne interferometry, where you have the separate recording of the wavefront and encoding, time encoding, and all that. When you get into the optical regime or the near infrared regime, you're still limited that you have to physically combine the light. There's not a way to encode because of quantum effects, and to operate fast enough, you're not catching enough signal for it to ever show up over the noise. So you kind of get this limitation of physics that you have to physically bring the light together. Until there's a couple ideas on doing like quantum interferometry.
Mm-hmm. So I wanted to bring that up later on, but yeah, absolutely.
Yeah. But for now, you have to have the wavefront travel that entire path, and the problem is that like with our telescopes, we make sure that not only do they have the exact same number of reflections, the same angle of reflections, even though they're in different spots, because you have to maintain the polarization. So if you have a difference in polarization, you're going to lose your fringes as well. The biggest, like in going to the history of interferometry, like this was the same site where the first interferometer, the Michelson interferometer, was built for stellar interferometer, the 20-foot. And it was basically outriggers for the 100-inch telescope to be able to measure the diameter of Betelgeuse in around 1920. After that, they built the 50-foot interferometer. And that one never really worked well because mechanical limitations of the day. You just can't build a truss stiff enough that you can make it rigid enough that flexing and all that you're getting a signal. And what we do is this many stages of correction, like I said, with the carts and with the mirrors, is moving them, is that we're constantly doing active corrections for the path length. And that's where the challenge gets. If you want to, hook up with your neighborhood and set up all your backyard telescopes and run them, one, how are you going to get all the angles the same, all the same mirrors? How are you going to do it? Vibration kills you. It's just, different optical quality. There are many ways to not get fringes. Everything has to be absolutely perfect. That's part of what I like about astronomy is you've got to have optics, electronics, mechanics, everything working perfectly.
To the 100 nanometers or so. Like what is the...
You're tens of nanometers. You're in the fractions of
tens of nanometers.
Wavelength you're measuring.
Yeah.
So like jitter, one of the issues, is we have these moving parts, and every moving part has some jitter and backlash, and all of these mirrors are, before the alignment, all in motorized stages. And that means jitter and backlash and thermal effects. And, we see, like right now, the weather's just turned cold on the mountain for the first time of the season. So we went from, 80 degrees down to 30 degrees. And so everything is moving all the time. All the distances between all the mirrors is changing all the time. It's just extraordinarily difficult.
Right. And so really to go beyond what you have at 300 meters enters extraordinarily difficult terrain. Do you sort of imagine a limit? I'm sort of envisioning like you have a whole bunch of those trucks and you take them to the high altitude salt flats in Peru and then drive them around and then park them and telescope them and then connect them together. Do you sort of envision where it just becomes impossible?
This is actually where when I go to a conference recently, a couple conferences this year, where this is a main topic, like the VLTI, the other main interferometer in the Southern Hemisphere. They're looking at, what they could do if they had another telescope, another UT, another 8-meter telescope on another mountaintop. What could they do? And, like I said, vacuum tubes are just cost prohibitive. It's a huge amount of infrastructure to build. Fiber is a possibility, but fiber has its own challenges. You don't get many losses over distance, but you add dispersion and stresses on the fiber. A tiny twist in the fiber that's different between one and the other is going to mess you up, unless you have to compensate for that or track it. One of the ways being looked at would be similar, kind of an offshoot of adaptive optics, of open air beam transmission, and then use adaptive optics at the ground level to clear it up. So you beam the light across, you have a beacon at the ground level or a laser at ground level, and deformable mirrors to compensate for all the turbulence in the open air. But then, the atmosphere is much thicker. The nice thing with looking up is there's most of the distortion of the wavefront is happening way lower down because most of the atmosphere is pretty thin. But when you're going long distance over ground level, that's not really been tried much. So this is kind of in the discussions among astronomers of what do we want to do in the next 10, 20, 30 years? Where do we focus? These are kind of the cost-benefit analysis and pros and cons lists we're making.
But it feels to me like, I'm sort of envisioning, right? You're firing this laser. The laser is acting like a guide star, but you're going through the soup of the atmosphere. You're compensating your mirror. You are measuring the distance. These all sound like the holy grail to astronomers, right? Like, would you like a telescope that has the light gathering capacity of 10 meter telescopes, but they're separated by 10 kilometers? Yes, please. Right? Of course they do. And so then is it that people just go, it's just not possible. There's no way, it's infeasible. Let's not continue to investigate it. Or is it that, that we're sort of in the early stages of this even being feasible with the new technologies that have come online?
Well, there's a good white paper on this. Was called the PFI, the Planetary Formation Imager, and that was an idea of what would be our ideal, justified by the science. Right. First, you list your science goals. Here's the things we want to know. Then you see, well, how do we build an instrument to do that? And it would be something like 10 or a dozen 10-meter telescopes separated by kilometers, and then doing beam transport. And you can make some trade-offs, right? With an interferometric telescope, like our field of view is about a few arc seconds. So you don't need to worry about, like, if you're building something like the Rubin telescope where you're doing large field, you've got, if you've ever done any optics, that the edges of the field are the places where all your problems come up. If you're doing a narrow field of view, it gets a little easier. So there's ways you can bring the cost down that way. The tricky part is not just the telescopes, though, and the separation. That is arguably easy. The longer your separation, the more delay control you have to have. So like if we expand to the kilometer baseline, that means our optical compensation lab needs to either get much longer, or we need to introduce more reflections and do more passes along the carts. So adding in more reflections, which lowers your sensitivity. So it's always you're stealing from one thing and gaining here. But as to limitations, like I said, it's resource limited. If we had a in a different timeline where it's like, hey, yeah, let's do this Apollo type, or even a smaller scale, like build a national observatory, a national facility, and do imaging of these things, like imaging exoplanets directly. It could be done. There are technological difficulties, but nothing that's a complete game stopper.
Mm-hmm. Is anyone else working on these larger arrays? I mean, anything in Europe, anything in China?
VLTI is the main one, right? The VLTI is the Very Large Telescope Interferometer. They're looking at potentially expanding in the future. They're so that's the main one. China,
are they invisible, or they're mainly in infrared, aren't they?
Mainly in infrared, yeah.
Yeah.
So like H and K band, I believe, and some longer. We do R band as well, so that gives you a resolution bump. Currently, there's Magdalena Ridge Observatory is another large interferometer. They just recently got their first fringes, and they've also had challenges over the years in getting up and running. But now we're very happy they've got fringes. But that's kind of it. There's not many interferometers, and
nothing in China.
Not in the optical that I know of. I know they've done a lot. They've maybe looked at radio, but it's not something I've kept track of.
Yeah, I haven't seen anything either. So
last I heard, it's like they're working on big radio telescopes. Was a primary thing for them.
Now, the obvious application, the place where most of your problems go away, is to go to space.
Mm-hmm.
Back at the turn of the century, the next big step after Kepler was going to be the terrestrial planet finder. And this was going to be probably a space-based interferometer where you had multiple telescopes flying information, combining their beams, giving you that high level of resolution. And I think as development of James Webb became more and more complicated, more difficult, they could see the costs were running up. They went, that's just going to, there's even more risk in the terrestrial planet finder. So 2011, they shut down that mission, and we haven't heard from it since. Now there's other ideas. There's the Habitable Worlds Observatory. There's the Life mission. Is it time for a space-based interferometer?
There's a few options. There's also there's I've seen proposals for preliminary proposals for like an interferometer on the moon.
Yep.
Like Gerard Van Belle has been talking about this, and then
I interviewed him about that.
Yeah. I think part of it is a timing thing. Formation flying is incredibly risky and not well demonstrated yet. There are a lot of challenges if you make like something like SIM, where it is a truss or a single large interferometer. Again, you still have problems of vibration and flexing. These are all things that could be solved. One of the best ways to test this early on I saw was Betty, which was the balloon-based interferometer. Because then you're going to get the best of both. If you can test something while it being, space-like, but you can still bring it back down and correct things. Unfortunately, it had a mishap. We've got colleagues out of University of Michigan, John Monnier has looked at like formation flying of drones to test and to demonstrate as technological demonstrator that we could, before going to space, demonstrate that we could build an interferometer on flying drones. And if you can do it with that vibration, you're set.
Wow.
Yeah, there's a
Like
lot
an
of
optical or even infrared interferometer flying on
yeah,
drones.
Yep.
That's crazy. I hadn't even thought of that.
Yeah, it's a great idea, and he's had some funding to do that. Small project. Um,
Yep.
what I think is, it's an incredibly interferometry is a well proven. It's a very promising technology. For a while, in all our meetings, there was often people saying, interferometry is inevitable. You can't keep building bigger and bigger ground base. You run out of land. Look at the challenges for TMT, for sites. It's just not feasible to build, a 100-meter telescope, single aperture, and then you still don't even have the resolution we have. So we've got to do something different. I'm a big fan of space and ground-based. I don't think you can do all of one or the other. They do entirely different jobs. And also, one of the things we've benefited from is the CHARA array now is an entirely different animal than it was 10 years ago and then when it was built, because we can continually upgrade. We are constantly working on things, both for maintenance and upgrading as we replace things. So it's a living creature. And you can't do that in space. You got to do it perfect once, and that's all you get. It's great for that. You have a very specific question you have to answer, and you go and do that, or you do a large survey of the whole sky, like something like TESS. But for ground-based, it's really observatory is a huge endeavor and a resource, because you're training people, you're building new instruments, you're building new collaborations. It's often multinational. I think it's a great investment. When I started, going into conferences and talking about, hearing about interferometry and coming out of the CHARA array, interferometry was around, but it was the same group of people. It wasn't very wide in the community, and it was kind of a black box. You did your thing, and there's some data reduction code, and if you weren't an interferometrist, you had no idea how it worked. Seeing now that like your audience is asking about interferometry is huge. It's just kind of skyrocketed in how popular it is, and I think it's become ripe. Now, when I go to any astronomy conference, they're regularly presenting results from CHARA, results from VLTI. It's not looked at as, I don't know if I trust it. It is very much like, well, the interferometry says this. These are, we have HR diagram where all of the stars are precisely measured. 700 stars to a very precise diameter on an HR diagram is hugely useful. Ashley Elliott at LSU has been working on that with Tabitha Boyajian. And so it's definitely time. Again, it requires investment. And like you said, I think interferometry and the CHARA array have been under the radar for a very long time. We've just kind of been here chugging along. But it's why I came to Georgia State, was I heard about the CHARA array and it seemed like a cool place to work.
Yeah. Yeah. You said my audience is interested. I would describe them as obsessed.
Great.
And I think it's just because as you said, it feels inevitable. It feels like that's where the progress continues. And we can see that we have things like the extremely large telescope. You've got a 39-meter telescope, and that's really at the very limits of what you can build a ground-based telescope. And we don't even know if it's going to work.
Our shortest baseline is 34 meters. So our shortest baseline is already an ELT solution.
Yeah. Yeah. And then, people thought that maybe you could build a 100-meter telescope, and that project was canceled. And so we go to space. And then we've seen the results from the Event Horizon Telescope, the incredible high resolution images of supermassive black holes. And you're looking at regions that are just ridiculously close. And yet there it is. So, and so it sort of feels like it will progress, and that funding will eventually find its way into larger and larger interferometer projects. Nic, what are you obsessed with right now?
Right now, keeping the array running and improving it everywhere. Like, it is, working at an observatory is a very service oriented in a way. Like our day to day is mostly spent making sure that night observations will go well. And so it is my main focus is, like I said, the array, a lot of it was built 20 years ago. It's been incrementally upgraded, but a lot of the stuff now it's changing so fast. Things that were custom built PCBs and custom, EEPROMs, all coded in assembly, can be replaced by an Arduino and do it all in C code. So switching the array out to more modular components, more easily replace things, just to make it so it moves smoother and faster in every way. Because we've added so much complexity. It was never originally designed to have, adaptive optics. And we have 12 adaptive optic systems all running simultaneously, 6 at the telescope and 6 in the lab. And that's just an insane amount of work. And we're always right at the edge, whatever motor you have, you're always right at the edge of its backlash limit, right at the edge of where, it's, if only it was twice as good, our life would be easier. We're never happy, it's
Yeah, but that's got to be tricky that you're trying to balance just helping an astronomer make their night's observing run with trying to figure out and implement ways of improving the array without getting in the way of the astronomers that are trying to complete their observation runs.
Yep.
And in many cases, the part that needs to be upgraded or fixed, but it's going to take the whole thing offline for a couple of weeks while you implement it. And then that means people can't use the telescopes.
Yeah. And now with so much focus on imaging, we need all 6 telescopes. The earlier days of the array, it would be, we're going to use these 3 and these 2, and there's a telescope that's going to be not used for a few nights. We could do work on it. Now, the demands on the array are very high, which is great. It's a good sign, but it means time for all these improvements and maintenance is a scheduling challenge. I spend a lot of time thinking about single point failures and where to replace those.
Yeah. Well, Nic, thank you so much for taking the time to chat with me today. Good luck with the array and with the mobile addition to the array, and then the future 1,000-kilometer space telescope made of 50 separate satellites orbiting in perfect formation and showing us the newspaper on an alien planet.
Yeah, I want a telescope on all the mountains in the San Gabriels, all connected by fibers. And also people, if they're in the Los Angeles area, Mount Wilson is open to the public. People can come up. There's a couple.
Yeah, it's very accessible. Just don't stomp around too loudly.
As long as daytime.
At night.
Yeah.
Well, Nic, thank you so much.
All right. Thank you.
I hope you enjoyed this conversation with Nic Scott. Now, we had a much larger conversation where we talked about instrument design. How do people working in this field listen to the needs of the scientist, upgrade their existing instruments, as well as come up with more novel, unique, out-of-the-box ideas to be able to solve specific scientific problems? Now, that larger version of this exact same interview is over on Patreon. Now, you can go click a link in the show notes down below. Go over and watch that one. It's completely free. There's no ads. You don't have to sign into Patreon or pay us any money or anything. You just can watch it over there. I'll put a link in the show notes. I'm going to give you some final thoughts, but first, I'd like to thank our patrons. Thanks to Abe Kingston, Barry Lake Roofing, Brian Bodie, Caradwin, Chuck Hawkins, Commander Baylock, Cy Nielsen, David Verbaff, David Gilton, David Matz, Evan Pro, Greg Feely, Hudson Moore, James Clark, Jeremy Matter, Jim Burke, Jordan Young, Josh Schultz, Marcel Smits, Michael Purcell, Monzo, OneStepForAnimals.org, Paul Robach, Rankaidu, Richard Williams, Sean Sargent, Stephen Fowler Munley, Team 49, Telescopes Canada, Vlad Chiplin, and Wolfgang Klotz, who support us at the Master of the Universe level, and all our patrons. All your support means the universe to us. Well, I'm really glad I was able to do this interview with Nic. He was able to answer a lot of my questions about the CHARA array specifically, as well as just interferometers in general. And I know that this will not be the end of it. That we will continue to be obsessed collectively about interferometers, and we will hold in our hearts waiting for that day when a space-based interferometer finally flies and gives us some of those possible applications, but out in space. It's really surprising to me how small the field really is when you consider that this is sort of the inevitable future of astronomy, that you're really limited by the forces of gravity on how big of a telescope that you can make. Taking these things, separate them, building these larger baselines is the obvious next step. And yet we're not seeing a lot of these projects that are being developed around the world. But hopefully that'll change. I guess maybe that's my part, is to help encourage and get more outreach to ideas that are sort of the next stage in astronomy development. Now, for those of you who do live in Los Angeles, you're probably familiar with the Wilson Observatory. I've been to LA. I know you can see the observatory from various parts in Los Angeles, but take a weekend, go up and check out the observatory. And now when you're there, focus on looking for the CHARA array and learning more about that, and tell them Fraser sent you. All right, we'll see you next time.